Can you see that?
Yes.
Okay, that's great. Yeah, first I want to express my great appreciation for the invitation from Professor Subra Lakshmi and Professor Saha for inviting me to give the talk here. And it is really my great honor. First, I want to say something about the talk today. So today, actually, I'm going to give pretty much a summary in AI machine learning in 5G spectrum sharing security on actually the state of the art, and also this pretty much including what we are doing and also what the research community has been doing. So by saying that, first, actually, this talk is pretty much different from all the previous talks I have done in IEEE, in the sense that previously my talk is mainly based on one research paper, basically done by myself and my students, focusing on one specific problem formulation and one research problem and the solutions, the mechanisms we are taking to solve that. But this presentation actually is more towards the general descriptions of say what's the current state of the art of using machine learning and AI in 5G spectrum sharing security, and also mainly from quite lower layer perspective, say physical layer and MAC layer. So that's pretty much the focus of today. So by saying that, well, this pretty much just serves as the general outline for my today's talk. So first, I give you the general descriptions of what, for example, the typical security problems we identified in 5G spectrum sharing. Mainly, actually, again, from a lower layer perspective, we are not trying to provide a very complete scope of description on machine learning and AI for spectrum sharing security. And so it's mainly from physical layer and the MAC layer perspective. Then we are talking about how actually what efforts people have done by using AI and machine learning in tackling security problems in spectrum sharing, and also what challenges we're facing, possibly what we need to do from research perspective in the near future perspective. So this actually is provides a high-level outline for my today's talk. So you can stop me anytime if you have any questions to ask. So first, this is a big picture in terms of 5G spectrum sharing paradigms. So we talk about 5G spectrum sharing, but spectrum sharing itself is not a new concept. So when we move to 5G, we say, okay, what are new? For example, we have done, for example, cognitive radio network in the past, say, 20, 30 years actively. So when we come to 5G, today's network, so what are the new, for example, spectrum sharing paradigms, and what are the related spectrum sharing security issues and how to tackle them? So we mainly actually look at today's spectrum sharing paradigms from 4 angles. So the first one, cognitive radio network. So this actually is pretty much what we have done like what I said in past 30 years. So sensing to full access by exploring the spectrum whole, opportunistic spectrum access. So this is very much a generic context of doing spectrum sharing. But when we go to come to 5G context, so we talk about specifically say, okay, different spectrum sharing paradigms, such as licensed shared access and or spectrum access system, depending on US or European terms. So mainly it's a database assisted spectrum sharing in the licensed band, such as 3.5 gigahertz. And another one mainly is on unlicensed band. So it's LTE in unlicensed band or LTE licensed access to access. So in this case, this coexists with the current Wi-Fi system, mainly based on duty cycle, this configuration, or listen before talk configuration. And another one is quite new today, and we also consider that as a 5G spectrum sharing scenario. So this one is ambient backscatter communication. So basically it uses the surrounding signals broadcasted from ambient resources or sources to communicate with each other. So this actually is also a kind of spectrum sharing, but in a very, very low power and low actually data rate perspective. So this is symbiotic with the existing system by modulating and reflecting surrounding ambient signals. So this basically are 4 different paradigms we are thinking about for today. Of course, we have some other scenarios here and there, but we actually try to group them into those big paradigms. So by saying that, we all know that basically, well, of course, again, I want to emphasize different spectrum sharing, they have different specific ways, steps to take. But in general, still, we try to follow these key steps, the way to characterize them. The 4 key steps in spectrum sharing. First, you have to be aware of the spectrum. So that's a spectrum awareness. So you can get the spectrum awareness typically, for example, traditional through sensing. So detect the unused spectrum and find possible opportunities for secondary users. Or another one is based on, for example, database and policy. So you don't have to sensing instantaneous, you don't have to sense the environment instantaneously, but you more or less can based on database or policy offered by the network, for example, or nearby either devices or other edge servers to provide you the rules or the build-up database for you to get aware of the environment. And then once you are aware of the environment, then you can go ahead and do spectrum allocation. So we borrow some existing terms, but this, of course, this spectrum allocation itself can be understood in different ways. So basically, in general, it helps whoever wants to share the channel to choose the best available channel based on the spectrum awareness. Then based on the allocated spectrum, so now you need to develop a specific, for example, resource allocation, scheduling mechanisms, or some medium access control schemes, contention-based, non-contention-based, for example, and to get fair access of the spectrum. So another one is spectral mobility. So basically, you need to users appear dynamically, and they come and go. So basically, and the need to have the shared spectrum also changes from time to time, from location to location, also from user to user. So basically, this provides the mechanism to perform the handoff or the dynamic switch on and off to available spectrums. So this basically, are for the typical ways for us to use to characterize the key steps taken in spectrum sharing. So now we try to understand, well, what are the typical, for example, the problems or challenges, especially in today's spectrum sharing. That actually, well, because we would like to understand the problem mainly from a security perspective, for example. So we want to understand in general that the challenges we are facing today in this umbrella. So first, of course, the one of the challenges comes from the fact that the secondary users usually lack of ownership of the spectrum. Well, again, really depending on what kind of spectrum spectrum sharing paradigm we're using, but typically, yes, secondary user or the user who share the channel, they will put into more secondary position. So lack of ownership of the spectrum, and also a lot of times, depending again, what spectrum you are sharing, a lot of times primary users, they have sensitive information they don't really want other users to get to know. So this actually, for example, the licensed sharing in US, actually, we have some kind of the spectrum actually originally owned either by, for example, military or some other usage. They actually are quite sensitive, carry lots of sensitive communication purposes. So how to protect those users, and that actually is very important from a spectrum sharing perspective. And then dynamic spectrum availability, because our environment, first, spectrum availability is very dynamic. It's kind of a stochastic And also the network, today's network, when we think about 5G, is very much distributed, heterogeneous, and heterogeneous from all kinds of perspectives. So those create lots of dynamics and also lots of uncertainties, I would say, for the spectrum sharing, how we tackle those uncertainties and how to, for example, identify those uncertainties, model these uncertainties, and take those, the knowledge of what we build about the environment into this spectrum sharing process. And of course, fundamentally, wireless broadcast nature that in general, that gives lots of challenging wireless communication. But of course, additionally adding this difficulty in spectrum sharing, because everybody who, no matter secondary, primary, or either both as, equal ownership of the spectrum still, they actually how to protect each other from either signal quality perspective or signal quality in terms of SNR, for example, or signal quality from security privacy perspective. So they all create lots of difficulty or challenges. And of course, complexity of the sharing environment that actually can be always understood together with this wireless broadcast nature. So that's what we are saying. Spectrum sharing in general, we say adds functionality and complexity that raise additional security concerns. So here, typical security and privacy issues people have identified in spectrum sharing, again, from lower layer perspective. So traditionally, we know that the typical security issues in spectrum sharing include, for example, spectrum sensing attacks. We try to understand that from, for example, the spectrum sharing the steps. So at each step, actually, there are different attacks. So sensing step, the first step is spectrum awareness. So the spectrum awareness, during the sensing, so you have this spectrum sensing attacks caused by primary use emulation and the spectrum sensing data falsification. And then if you build on your spectrum awareness based on, for example, database or inference, then your database and this inference could be subject to attack as well. And also, from the physical layer perspective, when you have, for example, spectrum access, you have spectrum allocation and spectrum access. Both procedures are subject to, this actually have been done a lot in the general wireless communications, but of course, in the spectrum sharing, this could cause problem as well. So spectrum access denial of attacks that includes, for example, jamming, eavesdropping. So now we try to understand, say, okay, if we are facing those different attacks, then in today's, for example, 5G spectrum sharing paradigms, how those different attacks can be modeled or tackled. Especially, we are interested in from machine learning and AI perspectives. So I'm not going through those. I believe all of you are security experts. So those are basically just some of the definitions of those different attacks. So primary use emulation, basically attackers try to emulate primary users' behavior during the spectrum sensing so that, it can actually exclude the legitimate secondary users by actually fooling them, saying that, okay, the channel is currently taken by the primary users. Of course, it can cause lots of problems such as service degradation, denial of service, connection unavailability, unreliability, and waste of bandwidth. So, usually the key strategy to take to deal with primary use emulation attack is to first, you need to identify. So a lot of research mainly focus on how to detect the primary user attack. And the mechanism to defend those kind of attacks, basically, so once you detect those kind of attacks, so main defending mechanisms basically is to exclude. Once you detect them, you just exclude the signals from for example, from the detected signals. So similarly to spectrum sensing data falsification attack, so the main research focus has been dealing with how to identify those attacks. So this actually is the most commonly seen attack in spectrum sharing. So basically, lots of, for example, secondary users, they are participating into this sensing process, but some of them actually try to form and send the falsified sensing data to the fusion center, which could be, for example, affiliated with the base station access point, and try to mislead others not to actually use the channel. So basically, the attacks can be classified just based on the current way we are doing research into 3 types: selfish, SSDF, and to gain exclusive access. So the user try to exclude others. They try to get the access to the channel just by themselves. So it just falsely reports the existence of the relative high PU energy, and while the PU actually does not exist in this particular case. And the second one is interference SSDF. So this one is falsely reports a low PU energy, which leads to other users to wrongly conclude that there is no PU existence. So they try to grab the channel, but now they cause interference to PU, and also they cause service degradation to themselves. So the third one is more like confusing SSDF. So this one just tries to disturb other users, secondary users, to prevent them from reaching the consensus by randomly. They don't send either consistent, say, oh, okay, selfish and interference, their goal is quite consistent. But confusing SSDF just try to send, for example, the randomly reporting true or false value of the PU energy to confuse the rest of the secondary users. So to defend the SSDF, first, like what we say, you need to identify, detect the attackers. So usually, well, we identify, for example, several typical detection mechanisms, such as outlier method, make the judgment based on the current spectrum sensing data, and the reputation-based method using the historic spectrum sensing data to update sensors reputation. So here, basically, this actually is just, the research that has already been done in lots of different, for example, by using lots of different mechanisms, include AI and machine learning. And of course, there is another one, is not to attack the sensing process, but to attack the database that's actually shared with the secondary users or the users who want to share the spectrum. So in a database inference attack, malicious secondary users can obtain knowledge beyond that revealed directly by the database by using sophisticated inference techniques. So basically, this kind of attack harm users' privacy, especially in some database-driven spectrum sharing. And this one can also be used to attack, for example, distributed machine learning methods. Usually to defend against those kind of attacks, one viable approach is to obfuscate the information reviewed by the database, and different, for example, privacy preserving strategies have been proposed. So, well, those two actually, the spectrum denial of service attacks. So this basically, the strategies taken are very similar to what we have learned in the general wireless networks, jamming and eavesdropping. So jamming and eavesdropping more or less focus on physical layer security. So we will actually talk about, say, okay, how we leverage, say, machine learning and AI technologies, what people have done in using, for example, more learning strategies to tackle those kind of physical layer security issues, such as jamming and eavesdropping, as well as other security issues we just mentioned. So now, well, this basically the table, I don't want to go through that because I think the paper itself says clearly. So just summarize what we have used from machine learning and AI in the spectrum sharing category perspective. So we know that spectrum sharing, the AI machine learning in spectrum sharing, well, typically we're using either supervised learning, unsupervised learning, or reinforcement learning. So for example, there are lots of study focusing on using supervised learning, mainly actually in doing spectrum sensing, for example. They try to rely on the, for example, classification those kind of capabilities try to, for example, identify the existence of primary users, also, for example, identify the primary user emulation attacks, and also the sensing falsification attacks. So those basically lots of studies have been using supervised learning, and unsupervised learning actually are also used extensively in spectral sensing, but many they're used, for example, in clustering, grouping perspectives, in helping forming some kind of underlying, for example, network structure, for example, in more efficiently to facilitate the secondary user to access the channel. And the reinforcement learning, of course, has been used a lot. We know that in the spectrum access mainly, and also spectrum mobility, in helping make the decision, basically, when to access the channel, which channel to access, and when to stop sharing the channel, using the channel. So basically, yeah, there are lots of research that has been done in using AI and machine learning in spectrum sharing. So this one actually, we just used one of our recent study, for example, published lately, how to use the reinforcement learning, for example, in doing spectrum sharing. So we apply this mechanism. Well, I will not go through the algorithm details, but if you're interested, we can go through the papers referenced here. So basically, we try to establish this reinforcement learning in two different scenarios. One is non-collaborative, and one is collaborative sharing. So basically, in non-collaborative or independent Q-learning schemes, we have primary user, we have secondary user, and the secondary users, basically, they try to deal with the environment independently without getting knowledge from each other. But in a shared collaborative Q-learning scenario, we allow users, basically, secondary users, to share their access information among each other so that they can help each other to build more system-wide or wideband knowledge about the channel. So basically, we use this typical Q-learning process and build up this agent, which is the secondary user state, which is the channel that the user attempt to occupy, and action is the basically is the decision taken by the secondary user which channel to occupy, and also reward really depends on if the channel access is a success or not, depending on the rate it can get and interference from the existence of the primary user and interference from other users. So basically, this is more like a diagram of the independent scheme. So each user just try to deal with the environment by themselves and learn the environment through the single bit feedback from the base station. But collaborative, basically, it builds up a more collaborative feedback map, and which is shared among all the secondary users so that they can know more wideband channel occupation information in the past, and based on which they can make more intelligent decisions into the future. So basically, here we just try to share that how this reinforcement learning in terms of say both collaborative and non-collaborative modes, how well it performs compared with in different configurations. So basically here it shows, well, the green line, first, both actually can allow users to grab the channel. When time goes on, actually the training, we can see that more converges into the steady state. But if we compare collaborative versus non-collaborative, the green line is independent Q-learning. So this actually is more like we understand in the throughput perspective. So throughput perspective, it actually falls the lowest among 4 schemes. The other 3 schemes are all collaborative, but given different sharing interval, how often they share their access information in the past. The more frequent it shares, the more effective it is. So the top line is just shows the most frequent sharing of this feedback mechanism. And then when the sharing becomes less frequent, the performance just degrades when it goes to, especially in the training stage, Of course, when it goes to steady state, the difference actually gradually vanishes. So basically, we try to use this example based on our own study, just try to see how effective the reinforcement learning can be used in spectrum sharing. And also further, we want to see from the study how actually those kind of collaborative reinforcement learning by allow users actually doing certain collaborative, because this is really we would like to say the structure actually we would like to see in the future, because in the future we can see, especially when we have like those kind of edge computing infrastructure, we push lots of computing facilities into local users, for example, and they do their local training and based on their local knowledge about the environment, and but a lot of times, well, the sharing of the channel is more like a global joint effort. So they still want to build up those kind of collaborative efforts. So we would say, oh, this is more like they build a virtual cloud computing beneath actually the coordinating point. But in fact, they're really doing distributed learning about the environment. So we try to actually build upon those kind of assumption of the understanding that this is really what the future Internet of Things, mobile edge computing type of network is. So that's why we want to see the difference between this independent training and the collaborative training, how it works. Of course, we still try to understand critically in this kind of training, what kind of feedback information we would like to pass among different users, and how much communication overhead it may take, and how timely those feedback can be shared among different users so that they can do those kind of collaborative learning about the environment as well as control. So here, now we will go to security part, because we're talking about the general, spectrum sharing, what's AI machine learning has been used in spectrum sharing. Now we go to what kind of security problems or security studies we have used, that have been conducted by using AI and machine learning. So mainly I grouped that into 3 different categories, and the following presentation is based on these 3 threads as well. So first, how to use AI and machine learning in defending security and privacy. And that actually has been probably the most research, I would say, that have been done so far. And the second one is how to use AI and machine learning in attacking security and privacy, such as adversary, those kind of network. So you actually, your attackers are becoming smarter and intelligent as well because of this AI and machine learning capabilities. So how you attack security and privacy using AI and machine learning, then of course, based on that, how you further defend based on those attacks. And the last one is distributed AI and machine learning in protecting privacy and security. So first, defending security and privacy. So the ideas of defending either defense methods or defending methods mainly consists of attacks detection and the defending strategies. That has been said already. So detecting, we have said that you have to detect, for example, PUE, SSDF, jamming attacks, and detect, for example, eavesdroppers. So detecting usually is a classification method. A lot of detecting methods, well, of course, a lot of them are based on supervised learning, but a lot of them, research we have seen, of course, are based on unsupervised learning as well. And the defending for the different attacks, PUE, basically, we have mentioned that in our previous slides as well. Just try to detect and omit the attack signal from your detected signals. And SSDF, again, you try to remove the sensing results of the malicious users and lower the reputation degree of those different users. So jamming, you just avoid attackers by, for example, typical way is doing channel selection, or this channel selection could be, for example, in the time domain, frequency domain, spectral domain. We know that we have used lots of antenna beamforming technologies to dealing with jamming, either create friendly jamming or dealing with the malicious jammings. And of course, also code domain. And eavesdropping usually just increase the difference between the legal receiver and eavesdroppers. So for example, we try to maximize the secrecy rate by minimize the capability of eavesdropping's detecting rate. And also defending the attack is a strategy of the selection problems based on the states of the network environment. So basically, well, this is, for example, we try to use an existing study to say how to use machine learning to detect the problem. So this is a system structure used in the following paper. We try to use them as an example to see, okay, how effectively the machine learning mechanism can be used to detect both. Actually, in this problem is primary user emulation problem and also SSDF problems. So in this particular problems, you have primary user and a secondary user, but there is a primary user emulation attack, and there is actually a user that tries to provide the false sensing reports back to the fusion center. So basically, this provides a scenario that with the presence of malicious attacks, both from PUE and SSDF, and of course, on top of that, the network is built upon based on some specific configurations that allows more complicated wireless transmission environment, such as self-interference caused by full duplex channels, radios, and co-channel interference by allowing multiple secondary users to share this spectrum. So basically, we just try to go through what strategy they're using to tackle this kind of detection problem. So basically, this first is a supervised learning, and they actually use 3 base learners. First one is temporal convolution of recurrent neural network, and the second one is support vector machine, and the third one is reputation-based weighted majority vote. So 3 different learnings. They have pros and cons, and they actually implement that all in one as their base learners. But on top of that, they have a meta learner, try to actually combine those 3 different base learners together by using actually this linear regression method, then ultimately come up with the best learning result. So this is they have the training phase and they have the test phase. So basically use this to build up their first the model, then use the model to test the results. So basically, this like what we say, they use this method to basically try to detect both primary user imitation and also this sensing report falsification attacks. So those attacks, based on this machine learning capabilities, they're showing that, well, 3 different schemes individually, they're doing pretty good job individually. So for example, in terms, the orange bar is the is the detection probability, detecting the true existence of the private users with the existence of the 2 attacks. So of course, this blue bar just shows you false alarm probability. Basically, it says that, okay, there's no primary user, but there's no attack, but you just trigger the network to react. There is an attack. So that's false alarm. And also inference time, how long it takes for the inference. So basically, the message here says, first, even though you use 3 individual schemes separately as a supervised learning, it is still quite effective in terms of this detecting and the false alarm. But if you jointly use 3 learners by following for example, those kind of meta training, so basically you can increase actually the detection probability by a good margin, but on the other hand, you decrease the false alarm probability significantly without actually leading to a much longer inference time. So inference time is still comparable basically to at least just using, if you use, for example, this neural network training and this SVM training, and those 2 trainings, actually the inference time is comparable to the meta training. Of course, if you just use this majority vote training, the inference time itself is much lower because this one is the simplest training way. So of course, the benchmark scheme provided here is just use the simple majority vote So basically, given what we have configured in this particular scenario, this actually fails pretty much on everything. So this basically tells the first how efficient it is to use those supervised learning in this PUE attack detection and SSDF attack detection, and also further how people, for example, you leverage the capability of each learner and how to jointly exploit the benefits of all of them and further to improve the learning capability, but without causing additional complexity over here. So this basically is the message, takeaway message we can learn and or say from this particular paper. So basically, more importantly, how you defend, of course, detecting the attacks is important, but from the system perspective, you need to defend, basically defending in the sense of defeating your attacks. So this study basically shows how we use a defeating mechanism to actually change your attack, how to say that, change the attack problem into a problem that can help actually your users. So this is what has been doing here. For example, you have a user here. This user particular, for example, this user is subject to attacks which there is a smart jammer next to this particular user. This smart jammer actually tries to navigate the environment and then try to adjust its power high and low to achieve two purposes. First, number one is to maximize the attacking to impact on the transmitter here, and the second, try to save its own energy. And so this attack, we call that a smarter jammer here. But the user here tried to, for example, leverage this jammer signal and convert the jammer signal into something that helps actually the transmitter. So this basically is a typical way we use machine learning to, the research has been done by this particular paper, use machine learning to defend and defeat the attackers. So the system model here, basically you have a transmitter, then this transmitter can be actually doing energy harvesting from a nearby, we call that ambient RF source here. And depending if RF source is on or off, if it's on, for example, one typical action the transmitter can take is to harvest energy. And when the ambient RF is off, the transmitter can, for example, to take the action of transmitting. Or even though if the RF energy is off, so the user can actually, the transmitter can, depending on the nearby scenario, can actually harvest from the jammer as well. So that's why I use the jammer's transmit energy to do the harvesting instead of creating a signal that directly actually is jammed by the smarter attacker here. So basically, this system operation can say that's what basically has been briefly described in the previous slide. Say the ambient source is idle, the jammer actually does not attack the channel, for example. This is the condition. Then the transmitter can, for example, just transmit in the maximum energy. That's the best scenario the transmitter can have. But if the ambient RF source is idle, but the jammer attacks the channel, then the transmitter can actually adapt its rate. That's actually it's a traditional way of doing. But here, besides just adapt its own rate to transmit, it can also backscatter using the jammer signal, or harvest the energy, or stay idle. So basically, it can adjust, take different actions to respond to the environment. And another operating scenario is when the ambient RF source is active, jammer is not active. So the transmitter can choose to either backscatter or harvest or stay idle, for example. And then last case is if the ambient is active and the jammer attacks, then the transmitter can choose to backscatter the transmission and or harvest the energy from both actually, or can stay idle. So those are different scenarios the system can operate in. So based on these different scenarios, of course, this is again is a reinforcement learning. They define a state space, So for example, in this particular case, the state space consists of 4 different states here. So first, the state of the ambient channel, active or not active, for example. And then J is the jammer state, active or not active. Then D represents how many packets in the transmitter. And then E represents the energy stored in the transmitter. So those are the states, state space used in this particular problem formulation. And action space, that is the action we have already mentioned in our previous slide. Say, okay, how many different actions the transmitter can take? The transmitter can take, for example, stay idle, transmit data, harvest energy, backscatter energy, or adapt its transmission based on for example, the scenario system operation scenarios by, for example, adapting the transmission power and adapting its transmission rate. So we actually here, let's understand in this way. So this particular paper, sorry, I'm not sure if I moved. Oh, this particular paper actually tries to compare this reinforcement learning with more traditional rate adaptation only mechanism. Then to see by adding traditional mechanism only works the 4th action here. 1, 2, 3, 4, 5, the 5th action here. But here, regarding the reinforcement learning, it adds more different actions, try to be more intelligent as a reaction to the environment scenario. So reward, this is the reward that has been defined in the particular scheme here. So basically, the reward itself, basically, it just shows for example, how much data it can be transmitted, and of course, on the other hand, with the assumption that it can store energy, for example, and minimize the energy consumption of itself. So the study itself actually is based on Q-learning, but it's an enhanced version of Q-learning. They call this like a deep dueling Q-learning network. Basically, the traditional Q-learning is very good in terms of dealing with network or system that has a small, for example, state space or action space. But when the action space or state space or the environment gets more complicated, convergence could be an issue. So then a different scenario of Q-learning has been proposed by trying to split the output of the training into value function and advantage function. Then actually based on this slight change of the traditional deep Q learning, then the convergence actually has been greatly improved in this particular training over here. So this is what has been shown from this particular study, and they say that this is more the comparison between the traditional approach. Traditional approach is the rate adaptation approach. Here is the deep learning approach. So the x-axis is the interference power from the jammer. So the jammer, with the increase of the transmission power of the jammer, the traditional approach just basically they have to back off. Either back off or subject to strong interference from the jammer, then so that the total throughput just keep decreasing. But with this intelligent, for example, reinforcement learning, basically by taking different actions to convert the jammer signal basically into something that can help the transmitter's transmission, either from energy perspective or, for example, by backscattering your transmission. Both can help actually the transmitter, so that we can see that with the increase of the jammer's power, actually the throughput of the transmitter does improve to a certain level. But of course, when it goes to beyond a certain level, the network throughput goes down due to the strong interference that really overwhelm the transmitter. So basically, here just shows different learning mechanisms. The blue line stands out. That's the proposal scheme by this particular paper. They just try to use the, well, for example, if just use the Q-learning instead of the proposed deep dwelling Q-learning, then of course the throughput goes down, mainly because the training inefficiency. because the training takes much longer time to convert. That leads to certain inefficiency of the training. And then some other schemes, it's not the proposal scheme, some other schemes used as benchmark comparison. So basically here it says that first, the two pictures combined together showing the efficiency of the share using reinforcement learning into the defending by taking different actions as a response to different system scenarios, and then more efficiently to bring up this primary user. In this particular case, it's just the transmitter, the throughput, overall transmission throughput, and of course at the same time to achieve energy efficiency, because the energy used here is really based on either from the ambient RF source or from actually the harvesting from the German signal as well. So this actually is from the detecting and defending using AI and machine learning. As what we have said, AI and machine learning can be used as attacking as well. So what we try to see here is, well, how attackers can use AI and machine learning to cause damage to the spectrum process. So for example, typically, just in general, AI and machine learning can be used to attack the users, or AI and machine learning can be used to attack the machine learning model itself. So here, there's another example just showing you if you, for example, if the attacker try to leverage the AI and machine learning, how effectively it can attack the spectrum sharing scenario. So for example, there is a paper here, we just use the paper here. So the paper here, you have, for example, the transmitter, and you have background traffic source, and you have a receiver, you have, this is attacker here. So this particular application of adversary deep learning to launch in what the paper says as exploratory attack on cognitive radio network. So secondary user first, for example, can build deep neural network model to predict if the channel is busy or not. And the training data includes the sensing results as features, then channel busy idle status based on the primary user state, for example. So the primary user is here, for example, this is the secondary user, and this is the receiver, and this is the adversary. Then the model is used by the secondary user to help make a transmission decision. That's what we have been pretty much discussed previously, how to help use AI machine learning. But in this particular case, the adversary user can build a similar powerful deep learning neural network classifier that can predict the outcome of the transmitter. Just by listening to the transmission, for example, the primary user's transmission, say when there will be an attack or not, if there is no attack, then this actually, the attacker can predict when the transmitter will have successful transmission or not, then try to falsify second user's input to the machine learning mechanism. Actually, this attack is very much different from the the previous PUE attack and the SSDF attack. The PUE and the SSDF attack, from a certain perspective, attackers are part of this secondary user group, but they try to maximize their own benefits. But here, this adversary user actually is not part of this collaborative secondary user group. It just, the purpose is to launch attack, just try to prevent the other users to use the channel. So this attack actually, the user just, the paper just shows a very, very typical setup of the configuration by this, based on the previous diagram. Then just showing the result just shows how effective the attack is. So for example, with no attack, based on the machine learning, the secondary user can very effectively to learn the channel access sensing, get the sensing information and access the channel effectively with the normalized throughput close to 99%. But just with 3 attacks, the paper just say, okay, if the user just launch 3 attacks, then effectively drags down the normalized throughput to only 3%. So this attack is very powerful because the secondary user actually Similarly, like the attack actually, similarly to the intelligent secondary user, it has this intelligence as well. Try to get to know the channel information, then just on time to block the secondary users to access the channel. So that's what it says here. This attack actually very much differs from the SSPF attack, since the adversary does not participate in the cooperative spectral sharing, cooperating spectral sensing. It does not actually form anything as a part of the joint report itself. And also it does not try to change channel labels directly, as in the SSPF attack. Instead, actually, its purpose is just to inject adversary perturbations to the channel to fool the transmitter into making wrong decisions. So this actually is just giving you an example to show how machine learning itself actually can be used. So to actually attack machine learning itself actually try to use to attack, not just to defend. So this raises the need of new defending mechanisms to protect wireless communications against intelligent attacks based on adversary machine learning. Okay. So this actually is the second topic, the threat in the machine learning AI in spectrum sharing security. So the first one is how machine learning and AI can be used to detect and defend. And the second is how AI and machine learning is used to attack. The third one is, well, we realize that there are so many attacks, there are so many security issues and also privacy issues, as well as, training itself usually, traditionally, happens, for example, in what we call the fusion center or a joint computing efforts. So federated learning as a new effort, well, it's not completely new, of course. It's been done in quite a few years, but we realized that it has been becoming a very powerful machine learning mechanism in spectrum sharing, as well as in some other tasks. Why? Because spectrum sharing, we know that the hybrid spectrum access needs very much collaborative and more autonomous spectrum sharing strategies that can be adapted to the environment and applications in 5G networks. And of course, the high resolution spectrum utilization data, well, we would like to have that. And on the other hand, it could be very difficult to get from both privacy, security, as well as bandwidth concerns. Like we know that lots of primary user information, due to high security issues, they don't really want to share those information to others. And also making inference on huge data requires lots of power. And also lots of, for example, large scale optimization, which actually become very much prohibitive from computation perspective, as well as from communication perspective, because you need to first convey those big data into a inference machine, which is more like, for example, a centralized inference machine. This actually, both from computation and communication perspective, very prohibitive. And a centralized strategy may not be appropriate a lot of times, actually, because our environment today, for example, is very much heterogeneous, distributed, like what we mentioned in one of the previous studies. So heterogeneous, distributed, this actually prefer lots of, for example, decision to be made locally, for example, and also computation to be done locally. So that's why combining everything together, we realize that spectrum sharing itself, first, of course, it needs kind of a joint collaboration, a more centralized coordination, but at the same time, a lot of decision, a lot of data in the future will most likely will be made locally. So federated learning becomes a good strategy, a mechanism actually to address all the needs over here. So we use this particular diagram here to show course, further learning how it is used in, for example, in building a what we call radio environmental radio map, for example, because we realized that spectrum sharing, instantaneous sensing, it is very helpful for you to know your environment, but it is very difficult for the local users to build up, especially, for example, when you go to future, say 5G, you have millimeter wave band. The bandwidth is huge. It's really a wide band. So how for a local user to build up the knowledge about such a wide band information from, for example, from different places? And so this actually becomes a very much challenging goal for the local users to achieve. So more probably, realistically, the local user try to leverage this federated learning and based on their local data sets. This local data sets could be local in the sense of geographic perspective, time perspective, and also from spectrum perspective. So you build up your local radio map, and then this local map, based on this local map building, and then they can actually pass that to a global model to actually create more a global picture of the radio environmental map, and then pass it back to the local users, for example. Then that can actually be understood in one typical way to use federated learning in helping, for example, spectrum sharing. So this actually, so based on this assumption, this is one of the study we have been used. We have conducted lately. So basically, we realized federated learning can be greatly used to facilitate not just computation, not just communication efficiency, but greatly help protecting the privacy of the local information. So that's why we, lots of studies along with this mainstream goal, we actually conduct this federated learning study, but combine that with some communication technologies such as non-orthogonal multiple access and adaptive compression and the specification of over the ear to see how we jointly leverage those different techniques to maximize the learning efficiency here. So this is the system model we use over here. So this is what we call a parameter center or a fusion center. So basically, this talks to different local devices. So different local devices, they have their local data first. The assumption is those different users, first, they're heterogeneous in the sense that they have different local data sets. So their data set is different. And it just emulates the environment. For example, like the radio, they have their local radio sensing information. And the second, the channel is different because they're far, they're close, and their local propagation environment is different. So from this sense, there are non-IID distribution of the local users. This puts some kind of, more realistic assumptions on the learning environment we're using over here. So this parameter user talks to different users in a sense, in two ways. First, local user does their local training and pass this trained model parameters to the fusion center using non-orthogonal multiple access. So it means that local users can be a part of, not all the users. We are not transmitting all the parameters back to the parameter center. So just selected group of users are transmitting their local training results to the parameter center by using non-orthogonal multiple access, but at the same time, by compressing their trained results because of this, because of the goal to achieve efficiency of this parameter updating. Because we want to use limited bandwidth in a limited time to get as many updates as possible from the local users. So the goal, this again, we use the supervised learning. So the goal is to, of course, minimize the training, the errors and the locally and ultimately at the parameter center to maximize or to minimize the global training errors. So basically, the problem, because we are using norma for uplink update, so we're following this norma, typical norma, successive interference cancellation decoding orders, and then ranking the channel, and then try to come up with this update rate for each local users for the trend results. So basically, in order to maximize in the limited time, we actually in the model we say, okay, this is the limited time for your training. In this limited time, we want to get as many as possible the updates from the local users. So again, we as a trade-off study, okay, we use actually adaptive model compression. So we compress the results from the typical 30-bit floating point to a much lower number, say 16 bits, 8 bits, or even like 4 bits, for example, depending on what's the rate given, to see the trade-off between the training accuracy as well as this communication efficiency. So basically, the problem is formulated as this, well, because we believe that the more the users can be updated, then the more accuracy the training will be. So our goal is to basically try to maximize the weighted throughput, the rate of all the users, so that they can get more chance to be updated. And the second, they can update their training results with maximal, accuracy. Of course, the best accuracy happens with no compression, but there is a trade-off over there, because with compression, you can allow more users to update simultaneously. Without compression, you have less users to be updated. So there is a clear trade-off between over there. So based on all those assumptions, based on this optimization formulation, we developed this scheduling. So we don't go through this detailed scheduling algorithm. Basically, it's try to achieve, the scheduling is developed to achieve this particular maximization goal, and also power control, because we know that a typical challenging in NORMA is to do power control, because NORMA at the same time, on one hand, they maximize the throughput by allowing multiple users to share the same bandwidth, same channel, but on the other hand, they cause, we call that NORMA interference to each other. So you have to control this power very carefully within the same group, so that they cause less interference to each other, but at the same time, they maximize their own throughput. So this basically power control is developed to achieve that goal. So I'm just sharing this result here briefly. So basically, by using this NORMA based NORMA plus adaptive compression or quantization, we call that scheme, we can see that the testing accuracy can be greatly improved by just using, if there is no NORMA. For example, we use, say, OFDM or TDM or traditional FDM. So the testing accuracy is much reduced. So basically, it says that NORMA can, well, even with adaptive quantization, lowering down the accuracy of the update, but because of NORMA efficiency, it can actually greatly improve the testing accuracy over time. And also the testing accuracy is compared with more other schemes. All of them use NORMA, but they use different scheduling and power, because in this study, we propose different joint scheduling and power scheme. So basically, if you use different, for example, power control, different scheduling, they can achieve different testing accuracy as well. But the difference, of course, is not as much as between NORMA and the TDMA. That's the case. Of course, here the bottom line case is a random scheduling. It's just you randomly select the user without try to consider the efficiency, or without considering the mapping, the group mapping. Of course, the performance is not good. But if you carefully mapping users and carefully doing this quantization, compression, by adapting as many users as possible, then the testing efficiency ultimately could converge to pretty good level. So here, this is just how we leverage. So basically here, I try to emphasize try to actually use the federal learning to, for example, do this local detection. This is mainly for local detection purpose. So detecting, for example, existence of the primary users, and or detection of the attacks such as PoE attacks or SSDF attacks, but based on this distributed learning state of centralized learning, and also by leveraging more how to say, effective communication mechanisms such as NORMA and also such as adaptive quantization. But of course, we know that federated learning itself is more capable of protecting privacy and security, but itself actually is not perfect in the sense that it could be attacked by users as well. Why? Because smart users actually can based on for example, the stochastic gradient descent method, even though you just pass on the weights of your the training results, the user can still build up enough knowledge based on the history of your updates, get to know the original user information, even though the raw data information is not shared over the channel. So basically, how to well, this is just one typical attack, of course, but there are lots of other attacks. For example, your sensor itself, for example, well, it's not trustful. Your channel could be, for example, eavesdropped, your channel could be attacked, just like what has been done in any wireless communication. And your sensor could be untrustable. Why? Because your local information is highly, for example, private, highly secure. And your sensor, your server, well, it's not the sensor that the server that's actually the most trustworthy. And from that perspective, it still can try to, like what we said, try to actually come up with the knowledge on local data based on whatever passed to the sensor. So from that perspective, there are lots of course, other attacks that have been identified in federated learning. We actually, there are some good papers have been published. If you're interested, this is the paper now written by us. Again, this is the survey paper here. So if you're interested, you can take a look. But here we just try to give one recent study. So this basically 3 strategies in privacy preserving machine learning. Again, they can be applied to federated learning, of course, such as differentiate privacy by adding some kind of random noise into your data, which is sent to the fusion center. This can actually basically cause this kind of perturbations, basically, so that the server may not be able to detect what's the original data. But on the other hand, it caused certain training efficiency problems. And in some studies, actually, it says ultimately, depending on what kind of differentiate privacy or noise perturbation you have added to your data that has been passed to for example, the server, the convergence could become an issue. Accuracy could become an issue as well. And also, there's another one called the secure function evaluation. Just involve multiple parties. For example, the user-generated data are distributed across different data owners, and they can do this collaborative compute based on agreed upon function without leaking of information. So this particular case, well, yes, it works efficiently in certain scenarios, but cause, for example, computation perspective is more complicated because it needs the collaborative computing from multiple users. And of course, it adds communication overhead. And more importantly, it actually based on, it still relies on the traditional way, for example, of doing this kind of key sharing. Then your key could be subject to leakage as well. So here we just used one of the recent study actually published in this paper here to see how this study used, for example, compressive sensing to deal with these security issues. So the key idea here is, I want to go through that just quickly. So key idea is your local users, depending on your privacy needs, based on your location, for example, based on your particular category in terms of the nature of the users. So you can group users into local different, for example, small groups. So those different small groups can actually, each group can share the same spreading code. So this actually same spreading code can be applied to the local data. So what's sent to the central user becomes more like a superimposed information from each local group, so that the central user, the central server actually does have sufficient information to do this global model update, but does not have sufficient information regarding each individual user's data. So in that case, you will not be able to get into each local user to actually break this privacy issues. So the study just here shows the key idea is based on this first spread encoding idea, and then use compressive sensing doing this at the user side to do the signal reconstruction. So basically, the idea based on this idea, it shows first, well, by using this compressive sensing based federal learning, the accuracy actually surprisingly is just pretty much same as using raw data. So meaning, well, in the global, in the server side, even though you have the superimposed information basically, and without individual user information, but you update it, the training accuracy is as accurate as to the case that you have individual users information updated. So that actually is the first figure. Of course, by using this spreading code compressive sensing based method, your communication cost is much reduced as well. So that actually is shown here in the second figure. So in the second figure, it says that, okay, if your original federal learning, your efficiency stays in the bottom. That's the black line over here. But with compressive sensing based federal learning, depending on your group size, we can imagine in the best case in terms of the communication efficiency, you only have one group here, right? Everybody just using the same spreading code, generate superimposed information on one channel, boom, sent to the server. That's pretty much like the similar case like a NORMA, like a CDMA. And that's the best case, but of course, in that case, probably you will be sacrificing certain degradation of your global model update. So here it just shows, use different group size. So basically, the top one is you only have 5 groups locally. So that gives you the best efficiency. Then your group number, say if you have 20 groups, then your efficiency, as long as you have this, group, if every group has like more than one. Of course, if every group just has one user, then it's the same as no grouping. So as long as you have, certain grouping strategy here, then the communication cost is much, much less than the original. So the key takeaway message is first, you use certain protection by, in this particular paper, it proposed to use compressive sense, the spread coding grouping first, then spreading code strategy. Then the privacy of the local user has been greatly protected. Why? Because the paper used a metric, performance metric called mutual information. Basically, it characterized the correlation between the received information, the constructed information, for example, regarding each local information. So basically, it says that, well, with this kind of grouping, the mutual information between the reconstructed information and each individual user's information is very low. So from that sense, the correlation between the two is low, so that the server may not be able to get too much information from the aggregated message received here on each individual user. So that's basically the number one message. And the number two message is use those kind of distributed compressive sensing based local training. Your training actually accuracy could be pretty high in this particular configuration scenario. Okay. So that actually pretty much, I think, address all the 3 scenarios we just mentioned. To use AI machine learning to detect, defend, and use AI machine learning to attack, and then further how to use distributed AI and machine learning to help protecting privacy and the security, and then how to actually further to develop new technologies to improve distributed AI and machine learning in different categories. Of course, we truly believe that your AI and machine learning, similarly, like in the second category, can be used to launch attacks to distributed federal learning as well. So the conclusion here is, for the whole presentation here is, first, spectrum sharing adds functionality and complexity. We all realize that, to raise additional security concerns, given especially given, for example, today's 5G spectrum sharing scenario, in terms of such a huge wide bandwidth in millimeter wave, such a heterogeneous configurations, and huge variety of your local user configurations and heterogeneous network configurations. So all those actually add extra complexity to spectrum sharing, further add complexity and to security. So AI and machine learning can be used to effectively defend, but AI and machine learning can be used to attack as well. And of course, failure learning becomes a very powerful mechanism in the spectrum sharing to protect and defend. But on the other hand, also subject to lots of privacy and security concerns. So that concludes the presentation today for my talk. So then I give this back to Professor Saha.
Thank you so much, Professor Hu. It's a wonderful, wonderful talk, giving like a real good description of all the different kinds of work and categorizing them. It's been wonderful listening to them. I would like to take questions from the audience now, and please feel free to post your questions in the chat box here. So the first question comes from Moinul Hussain. Thanks, Dr. Hu, for the presentation. It is very helpful. As we know, the use of ML/AI requires significant computation power, and it is more complicated when we are dealing with mobile users. Can you please provide your views on how, number one question, how and from where can we provide or manage the required computational resource? And the second question is, do you see computing platforms, for example, edge or cloud, as essential supporting tools to solve the overall spectrum security challenges?
Yes, yeah, that's an excellent question. I truly believe the question actually, this particular question is, for example, is actually of my key thinking when I was working on this topic. So I truly agree with you that yes, machine learning and AI first, it is important, but ultimately it where the computation occurs, right? And how we actually get this done in today's network, because we are really dealing with a network such as massive users, and those massive users, actually a lot of them still lack of sufficient computation powers. So that actually, yes, a lot of study today, we started with assuming that, okay, AI and machine learning, yes, the computation occurs in some kind of centralized entity, which could be cloud server, and today more as edge server, right? Because we're talking about mobile edge computing. But ultimately, I think the trend is more like to push all the intelligence to really not just the edge, right? From cloud to edge, then from edge to device. That's pretty much, the goal of building the future network. So by saying that, we believe first the computing capability of mobile users will be greatly improved in the future. That's for sure. Even though today, lots of those local users, they still lack of sufficient either computation power or battery capability, but those will be greatly advanced in the future. So we hopefully, in the future, it will build up those kind of hierarchical computation infrastructure, cloud, edge, local device. So they all together actually will form those kind of computing, I would say computing power to facilitate AI and machine learning. But by saying that, the research has been, I have seen lots of research that has been done to facilitate those kind of, we call hierarchical computing infrastructure, especially how to, for example, design, like, for example, those kind of virtual distributed cloud. So what do you mean by virtual distributed cloud? Really, the computing is distributed to local devices, even like those kind of small sensors, small devices, which today we believe that they still lack of sufficient power. But in the future, they should be able to undertake certain computation, those kind of tasks as part of this hierarchical infrastructure. So in the bottom, we believe that we have those kind of so-called virtual distributed cloud, which consists of all the distributed gadgets, devices, and they all contribute jointly in a collaborative but distributed way to this AI and machine learning.
Just related to that question, I was also thinking of asking you this question that in your model, do you need all the users to participate to reach the accuracy that you need to, or you can have maybe like 80% or 60% users actually participate, and still you could probably get somewhere close to the accuracy that is acceptable?
Yeah, that's a great question. Yeah, that actually is one of the focus of the results we want to actually share in the paper. In reality, no, you don't have to have all the users to participate. It really depends because, for example, we do have the comparison and say, okay, you have 10% of the user, 20% of the user, 30% of the user who participate of the sharing, for example, of the updating process. Of course, you at a certain time you see the trend to go up, right? But till you reach, for example, I'm not giving this number as say that that's the number we reach the consensus, but depending on your different configurations, but till you reach like X percentage, actually you see the accuracy become more like centralized. You don't have the message is no.
That's what I was. So that way the computation can also be reduced to many of the low power devices as well, because they might not require to participate all the time.
Exactly. Yeah, it's really much actually, even in the study, for example, the results I'm showing here, we're not trying to update all the users like what we say. We select part of the users to update, and during that process, other users can just keep, well, they still do, for example, maybe other tasks, but at least they don't participate in communication part. Communication part is still a big part of the power consumption, right?
Sure.
So yeah, so no, and there are lots of mechanisms, algorithms that have been developed in selecting who to participate, for example. Yeah.
I have, I don't see any more. Oh yeah, there is one more question just popped up. This is from Yang Xiao. Thanks for the talk. What are the challenges on the data collection part on AI ML for spectrum sharing? For example, feature selection, adversarial example generating, etc. And can you share thoughts on what's the high-level process of gathering RF data, for example, IQ data, and compiling them for ML-based detection?
I try to understand the question. So what are the challenges on data collection part for AI and machine learning, feature selection, adversary example? And can you share the thoughts on what's the high level of gathering IF data? I don't know exactly how to answer this question, but in general, in terms of the data collection locally, yes, you probably have certain part of this local device in terms of what data to collect and how to process this data locally, and what data you want to share with others. I'm not sure if that relates to this particular question.
So I think the question might be leading towards experimentation. So when we are evaluating, how do we truly collect data for something like the one that you have shown, the kind of architecture that you have shown? Like multiple nodes, and then you have centralized server. So how do we actually collect samples over the air? In that sense, how to do actual experimentation and validate those results. So if there are any challenges that you might have faced, or what is the general challenges that one can face?
Yeah, I'm trying to think about, because my research itself, does not get directly involved of collecting data part. We're using lots of, for example, publicly available data. So, but particularly challenging in gathering, for example, IF data. Well, IQ data, I don't know exactly what's the process you can get lots of IQ data? Because IQ data itself, first, yeah, I believe the challenge is the volume is extremely high, and you need to have, I don't know exactly at which level. You need to probably go to, let me try to see the IF unit part to get all those IF data out. Well, I don't have a particular answer for this one. Maybe I can take this offline to talk with the question. But in general, yeah, getting data itself, I just try to share probably in the general sense. In the getting data itself actually is very challenging, and to access the data, this actually has been pretty much one of the top challenges we are facing today. How to well get the data and how to share the data with the general community. Because a lot of times, for example, one of the problems we're facing today is people, for example, getting the data and training the data based on a particular data set. But the problem is, well, when the trained model applies to a totally different data set, you may not be able to guarantee it will be successful. So then we probably try to get this, I try to see how to propagate the problem to one of the questions we have talked during one of the NSF workshops. So how to, for example, we have this like lots of different national-wide like powder test bed, how we can get those data collected and make it available from national, more general research community perspective. But in terms of exactly the process of gathering IF data, actually I don't have much to share because I have not myself actually have not done much research in terms of collecting data by myself. But I would be very, very interested in knowing that. And as a research process, that's definitely a good question. Yeah.
So, and related to that, I had a question that was very similar. So in general, when we do any kind of physical layer communication or anything that is in the physical layer, often it is easier to use the 2.4 gigahertz band because that's unlicensed, and then use Wi-Fi kind of transmissions because that's also easier to do than LTE, and then use indoor transmissions to show our algorithm. So use software-defined radios and work on those. However, for any kind of security or anything that are related to cognitive radio, where we are talking about wider bandwidths, not just 2.4 gigahertz, and also when we are talking about jamming or different other things, most of the universities don't even have something like a Faraday cage, right? So how do we actually show all of these different security aspects or security breaches or attacks or models that actually can prevent these attacks or still work around these attacks in an experimental setup? So I think that's still a challenge for many of the researchers in this field.
I totally agree. Yes, I think yeah, itself actually a lot of, because most of the studies we are performing today actually a lot of times we are just based on some simple configurations, not just like very realistic or experimental type of configurations. So by saying that, our, for example, access to a more realistic data set, a more realistic channel environment, a more realistic, attacking environment is still actually, I would say, quite limited. So how to, sorry, go ahead.
No, it was a different related question. So I understand that industry has a lot of experimental process before anything goes into 3GPP discussions, and there are more strong simulation platform that are used in the industry than what we use in academia. So my question to you is, can we learn, or what should we learn from the industry that we can take it from there and put it in academia? Experimental part is fine, but what can we do when we cannot do an experiment, realistic experiment? Are there stronger simulation platform that we can look at instead of writing a few lines of MATLAB code?
Well, yes, in the industry, actually, that was the part I was involved when I was in industry. That actually, the simulation platform built by, for example, like 3GPP, since you mentioned that, it's a very powerful platform, that's for sure. The platform itself, they have a very much detailed, they call it evaluation methodology to follow in terms of, for example, how to build a channel, how to build, for example, all those link to system mappings in terms of, say, from your channel environment to what kind of, in terms of what kind of modulation coding schemes, in terms of what kind of coding schemes reflect to bit error rate, and also going to, for example, wireless interface technology such as MIMO, such as all those radio access, coordination, scheduling. So they have a very powerful platform, that's for sure. But the challenging is because the platform is quite humongous. I can tell you that. So what we can learn a lot from that is I truly believe, well, you need to have a very much a good channel model. Because a lot of channel model we are using for academic stuff, like especially in MATLAB, they may not be realistic enough. So you have to realize, especially when you go to millimeter wave, the channel model is extremely important. And of course, in terms of how to simulate what they call a scenario, right? How you model the network. Because in our scenario, we would probably easily just like plug in, say, 3 cells, 4 cells, or just a simple interference environment. But in reality, the system deployment is way more complicated. It's not just like, okay, the like 10 cells, they just created in a homogeneous way. Today, we have a very much heterogeneous way to deploy the network. So how you actually emulate those kind of. So I think the more, I would say the challenging issues is how to you really model the link, the channel itself, and how you model the network, the system configuration, I would say. In terms of the scheduling, in terms of other things, you can simplify. I don't see any huge problem as long as it is not a standard submission work, right? It's more like research purpose. Then that should be fine, yeah. But channel and system configuration, that two parts, definitely we can learn a lot from what industry has been doing.
Great, thank you. I have one more question from Chiang Ni. Great talk. Can you give a bit more details about the collaborative DRL versus non-collaborative DRL? Also, do you have best strategy for designing collaborative DRL?
Well, I'm not saying like I have the best strategy, but we do have, yes, we do learn a lot from designing, for example, the collaborative. This D is deep or distributed?
I believe this should be distributed. Okay, deep.
Oh, deep, yeah. No, collaborative, well, collaborative in the sense that, yes, when we do this, for example, reinforcement learning, so basically, other users, for example, their past decision process and what they have learned and what they have gained can help tremendously others to build up a more global knowledge. So from that sense, the collaborative learning definitely, like what we present, it works better. And the more details really is regarding what kind of information you want to share with others. If it's non-collaborative, the user just deal with itself, says, okay, a particular channel, right? I just know this channel, this is what I accessed in the past. And this is what I try to access now. I only know my action information. But collaborative, basically, other people will tell you what their history information in terms of accessing the channel. So basically, you know more about a particular channel information. If this channel, for example, is accessed by another user in the past, then particularly, for example, if this channel is accessed by another user, but it is successful, then for another user, you may not be able, you may not want to use this channel for the current moment. Why? Because if that channel has been already occupied by another user. So that's directly reflected into your reward, the function definition, actually. So your reward function will be different. So you have more rewarding scenarios than just the non-collaborative, because non-collaborative, just success, fail, based on its own view. But collaborative really gives you more views, basically. If it succeeds, why it succeeds. It fails, why it fails. So basically, you have more rewarding scenarios, and that gives you more granularity in terms of defining your policy, basically. So have the best strategy. Well, I don't know what's the best strategy. So the best strategy, basically, collaborative needs to share with each other. So that costs lots of communication overhead as well. But on the other hand, I truly believe in the future, for example, like what I said, when we go to like a federal learning, in the future, the learning itself actually will be pretty much more distributed, but collaborative. So the best strategy is, well, there are lots of different strategies. I don't know what's so-called the best strategy, but when we design this kind of collaborative learning, we do have some critical information to share, for example, so that it can allow to bring up the overall learning efficiency as well as communication efficiency. So it's more lots of optimization, distributed optimization issue involved. That's for sure. But that's pretty much the trend. What I can see that it's more like a virtual distributed cloud.
So at this point in time, I would like to thank Professor Hu, and I really appreciate taking your time to discuss all the work that has been done and the challenges that we will be facing in recent years in terms of research. So once again, thank you for this wonderful talk, and we will, I hope we will be able to get the slides, right?
Sure, yes, I will share the slides. But at the same time, yeah, I think I appreciate very much the discussions, like what I said, because lots of research, we just started as well. So I would like to very much keep in touch with all the researchers and exchange our ideas. And yeah, hopefully we can learn from each other.
Yes, absolutely. That's the purpose of this series.
Yeah.
Thank you so much. And we will post the slides and the video in the SIG website. Thank you. Bye.
Yeah, thank you. Thanks again, Professor Saha.